This section covers how to protect data at rest. It's important to encrypt data at rest so that security of the data is ensured even if an unauthorized party gains access to it. Encrypting data at rest makes it much more difficult for attackers to compromise data, even if they can compromise an endpoint. Also, you might need to protect your data at rest due to business or compliance requirements. Let's look at the most common issues that make it necessary to protect your data at rest and how you can protect against each issue. First, to prevent information disclosure, limit the number of users who can access data and use policies to manage access to resources. Use encryption to protect confidential data. Next, to prevent data integrity from being compromised, use resource permissions to limit the scope of users who can modify data. Implement digital signature and encryption. If data is compromised, restore it from backup or a previous object version. To reduce the likelihood of accidental or malicious deletion, use the correct permissions and the principle of least privilege. If an issue occurs, restore data from backup or a previous object version. Finally, you want to ensure the availability of your system, hardware, and software. In the case of a system failure or natural disaster, restore your data from replicas. By default, all Amazon S3 resources, buckets, objects, and related sub-resources, for example, lifecycle configuration and website configuration, are private. Only the resource owner, meaning the AWS account that created it, can access the resource. The resource owner can grant access permissions to others by writing an access policy. You can modify bucket policies to allow additional access, and AWS provides a number of tools to configure buckets for a wide variety of workloads. For example, the S3 block public access feature acts as an additional layer of protection to prevent accidental exposure of data. In addition, consider encrypting data at rest in Amazon S3. Amazon S3 supports two types of access control mechanisms, identity-based or user-based, and resource-based. Let's look at the differences between identity-based and resource-based policies. They're nearly identical in appearance and function, but have some slight syntax differences. The biggest difference is where they are applied. Identity-based permissions are attached to an AWS Identity and Access Management, or IAM, user and indicate what the user is permitted to do. Resource-based permissions are attached to a resource and indicate what a specified user or group of users is permitted to do with the resource. For example, you can attach resource-based policies to S3 buckets, virtual private cloud or VPC endpoints, and AWS Key Management Service or AWS KMS encryption keys. Resource-based policies are a way to restrict access on a resource basis. In the example on the slide, an IAM user named Bob has an identity-based policy attached. The policy allows him to use the GET, PUT, and LIST APIs for bucket X. However, the resource-based policy for bucket X allows him to use GET and LIST and denies the ability to use PUT. This means that Bob cannot put objects into bucket X, even though his identity-based policy allows it. For bucket Y, Bob's identity-based policy allows the LIST action. The policy does not explicitly allow or deny the GET and PUT actions on bucket Y. The resource-based policy for bucket Y allows him to use GET and LIST, but does not specify the PUT action. Therefore, Bob can read objects from the bucket even though his identity-based policy doesn't explicitly allow it. Here are the key takeaways from this section. Encrypting data at rest makes it more difficult for attackers to compromise data. Data stored in Amazon S3 is private by default and requires AWS credentials for access. And Amazon S3 supports two types of access control mechanisms. The first is identity or user-based. The second is resource-based. Thanks for watching. This section describes data protection features that are available in Amazon S3. Amazon S3 provides a number of security features to consider as you develop and implement your own security policies. The Block Public Access feature helps you manage public access to S3 resources. By default, new buckets and objects don't allow public access, but users can modify bucket policies or object permissions to allow public access. S3 Block Public Access provides settings that override these policies and permissions so that you can limit public access to these resources. This feature provides 4 settings. The first is Block Public ACLs. This setting prevents any new operations to make buckets or objects public through bucket or object ACLs. Existing policies and ACLs for buckets and objects aren't modified. Second is Ignore Public ACLs. It's used to ignore all public ACLs on a bucket and any objects in it. The third is Block Public Policy. This setting rejects calls to put a bucket policy if the policy allows public access. Enabling this setting doesn't affect existing bucket policies. The fourth setting is Restrict Public Buckets. It's used to restrict access to a bucket with a public policy to only AWS services and authorized users within the bucket owner's account. These settings are independent and can be used in any combination. You can apply each setting to an access point, a bucket, or an entire AWS account. You cannot apply these settings on a per-object basis. If the block public access settings for the access point, bucket, or account differ, then S3 applies the most restrictive combination of the settings. When S3 receives a request to access a bucket or an object, the service determines whether the bucket or the bucket owner's account has a block public access setting applied. If an existing block public access setting prohibits the requested access, S3 rejects the request. In addition to these settings, the Amazon S3 console highlights your publicly accessible buckets, indicates the source of public accessibility, and warns you if changes to your bucket policies or bucket ACLs would make your bucket publicly accessible. Versioning in Amazon S3 is a method of keeping multiple variants of an object in the same bucket. With this feature, you can preserve, retrieve, and restore every version of every object stored in your buckets. By default, S3 versioning is disabled on buckets, and you must explicitly enable it. Versioning can help you recover objects from accidental deletion or overwrite. For example, if you delete an object, instead of removing it permanently, S3 inserts a delete marker, which becomes the current object version. You can always restore the previous version. Overwriting an object results in a new object version in the bucket, but you can always restore the previous version. With versioning enabled, the most recently written version will be retrieved by default. You can retrieve older versions of an object by specifying the version in your request. To customize your data retention approach and control storage costs, use object versioning with S3 Lifecycle. After you enable versioning for a bucket, you can't return it to an unversioned state. You can, however, suspend versioning on a bucket, which stops accruing new versions of the same object in a bucket. You might do this because you only want a single version of an object in a bucket, or you might not want to accrue charges for multiple versions. When you suspend versioning, existing objects in your bucket do not change. When working with S3 versioning in Amazon S3 buckets, you can optionally add another layer of security by enabling multi-factor authentication or MFA delete. When you do this, the bucket owner must include 2 forms of authentication in any request to delete a version or change the versioning state of the bucket. Finally, with object lock, you can store objects by using a write once, read many, or worm model. This feature provides protection for scenarios where it's imperative that data isn't changed or deleted. You can use object lock to meet regulatory requirements that require worm storage, or add an extra layer of protection against object changes and deletion. Note that object lock works only in version buckets. Object lock provides 2 ways to manage object retention. The first is retention periods. A retention period specifies a fixed period during which an object remains locked. During this period, your object is worm protected and can't be overwritten or deleted. The second way is legal holds. A legal hold provides the same protection as a retention period, but has no expiration date. Instead, a legal hold remains in place until you explicitly remove it. You can configure object lock in one of 2 modes. In governance mode, users can't overwrite or delete an object version, or alter its lock settings, unless they have special permissions. If you require stronger immutability to comply with regulations, you can use compliance mode. In compliance mode, a protected object version can't be overwritten or deleted by any user, including the root user in your AWS account. Here are the key takeaways from this section. Block public access ensures that objects never have public access now and in the future. Versioning preserves, retrieves, and restores every version of every object stored in an S3 bucket. And finally, object lock prevents an object version from being deleted or overwritten for a fixed amount of time or indefinitely. Thanks for watching. This section covers protection through encryption. Encryption is the process of converting plain text, readable data to an unreadable form known as ciphertext to protect it. For an encryption algorithm to be effective, it must be almost impossible to reverse without knowing the inputs to the algorithm. Inputs might include an encryption key. What are the differences between client-side encryption, or CSE, and server-side encryption, also known as SSE? The approaches differ in when, where, and who encrypts and decrypts the data. CSE means that your applications encrypt data locally before submitting it to AWS. Your applications also decrypt data after receiving it from AWS. Data is stored in an encrypted form with keys and algorithms known only to you. SSE means the data is encrypted at its destination by the application or service that receives it. The encryption process is transparent to the user. AWS supports both CSE and SSE. Client-side encryption takes place before data is submitted to AWS, and decryption occurs after data is retrieved from AWS. To enable CSE, you can use a key stored in AWS KMS, or use a key that you store within your application. With AWS server-side encryption, your source data comes from systems in your data center or an Amazon Elastic Compute Cloud known as Amazon EC2 instance. You can upload that data over an HTTPS connection to any of the AWS services that support automatic server-side encryption. The service endpoint handles the encryption and key management processes for you. You have three options for server-side encryption in Amazon S3. The first is SSE with customer-provided keys, or SSEC. You manage the keys, and S3 manages encryption and decryption. The second type is SSE with S3 managed keys, known as SSE S3. With this type, Amazon S3 encrypts the key itself with a key that the service regularly rotates. The third is SSE with AWS KMS keys, or SSE KMS. Amazon S3 uses AWS KMS keys to encrypt your S3 objects. This method uses envelope encryption to protect plaintext data with the data key and then encrypt the data key with a root key. In this scenario, AWS KMS is used to encrypt data at rest. This is an example of SSE KMS. The user creates a KMS key and uses it to encrypt objects that are stored in Amazon S3. Let's look at how encryption happens with this method when you upload a file to S3. First, you request to upload a file and store it as an encrypted object in an S3 bucket. Next, S3 requests a data key from AWS KMS to use to encrypt the file. Third, AWS KMS generates a plain text data key and encrypts the data key by using the customer-managed key. Then, AWS KMS sends both copies of the data key to S3. And finally, S3 encrypts the object by using the plain text data key, stores the object, and then deletes the plain text data key. The encrypted key is kept in the object metadata. Now, let's look at how decryption happens with the SSE KMS method when you try to open an encrypted object stored in Amazon S3. First, you request to open the object. Second, S3 notices that the requested object is encrypted. S3 sends the encrypted copy of the data key that the object is encrypted with to AWS KMS. Next, AWS KMS decrypts the data key by using the customer managed key, which never leaves AWS KMS. AWS KMS sends the plain text data key back to S3. And finally, S3 decrypts the ciphertext of the data object, allows you to open the object, and deletes the plain text copy of the data key. AWS KMS provides the ability to create and control the keys used to encrypt your data. You can create data keys with unique aliases and descriptions, automatically rotate your keys on a scheduled basis, and disable or delete keys. You can also import your own keys instead of using AWS-generated keys. The service uses FIPS 140-2 Validated Hardware Security Modules, or HSMs, to protect keys. AWS KMS is integrated with other AWS services to help protect the data stored with these services. And you can set usage policies on keys to determine who can use them and under which conditions. Amazon Elastic Block Store, or Amazon EBS, encryption is an encryption solution for EBS resources associated with your EC2 instances. You aren't required to build and manage your own key management infrastructure. EBS encryption uses KMS keys when creating encrypted volumes and snapshots. Each volume is encrypted using AES 256 XTS. The data key is encrypted under a KMS key in your account, and EBS must have access to this key. Let's look at the steps to encrypt and decrypt EBS volume data. First, EBS obtains an encrypted data key under a customer-managed key through AWS KMS and stores the encrypted key with the encrypted data. Then, the servers that host EC2 instances retrieve the encrypted data key from storage. Third, a call is made to AWS KMS over TLS to decrypt the encrypted data key. AWS KMS identifies the KMS key, makes an internal request to the HSM to decrypt the data key, and returns the key to the customer over the TLS session. And finally, the decrypted data key is stored in memory and used to encrypt and decrypt all data going to and from the attached EBS volume. EBS retains the encrypted data key for later use in case the key in memory is no longer available. Here are the key takeaways from this section. AWS supports both client-side and server-side encryption. With CSE, you encrypt your data before sending it to AWS. With SSE, AWS encrypts data on your behalf after receiving it. AWS provides 3 types of SSE: SSE-C, SSE-S3, and SSE-KMS. AWS KMS can create and control the keys used to encrypt your data. That's it for this video. Thanks for watching. This section covers how to protect data in transit. Data in transit is actively moving from one location to another, such as across the internet or through a private network. To protect data in transit, you protect data while it's traveling from network to network or being transferred from a local storage device to a cloud storage device. Wherever data is moving, protection measures are critical, as data is often considered less secure while in motion. When data is in transit, what risks is it exposed to? Accidental information disclosures, data integrity compromises, identity compromises, which include man-in-the-middle attacks, and identity spoofing. A man-in-the-middle attack is a form of cyber attack in which criminals exploit weak web-based protocols to insert themselves between entities in a communication channel to steal data. This type of attack makes the network vulnerable to packet sniffing and modification. You can protect data in transit by using Secure Sockets Layer, or SSL, or client-side encryption. You can securely upload your data to or download it from Amazon S3 through SSL endpoints by using the HTTPS protocol. You can limit access to an S3 bucket from a specific Amazon Virtual Private Cloud or Amazon VPC endpoint or a set of endpoints by using S3 bucket policies. To protect data in transit, AWS encourages customers to use a multi-level approach. All network traffic between AWS data centers is transparently encrypted at the physical layer, All traffic within a VPC and between peered VPCs across AWS regions is transparently encrypted at the network layer when using supported EC2 instance types. At the application layer, customers have a choice about whether and how to use encryption by using a protocol such as Transport Layer Security, or TLS. All AWS service endpoints support TLS to create a secure HTTPS connection to make API requests. Protecting data in transit includes protecting remote connections to servers. Users who access Windows terminal services in the public cloud usually use the Microsoft Remote Desktop Protocol, or RDP. By default, RDP connections establish an underlying SSL or TLS connection. For optimal protection, the Windows server being accessed should issue a trusted X509 certificate to protect from identity spoofing or man-in-the-middle attacks. By default, Windows RDP servers use self-signed certificates, which aren't trusted and should be avoided. For Linux servers, Secure Shell, or SSH, is the preferred approach to establish administrative connections. SSH is a protocol that provides a secure communications channel between the client and server. SSH supports tunneling, which you should use to run applications such as X Windows on top of SSH and to protect the application session in transit. By default, Amazon Machine Images, or AMIs, that AWS and most vendors from the AWS Marketplace provide don't allow the root user to log in from an SSH terminal. The default configuration for AWS-provided AMIs is logging in with an SSH key pair with password authentication deactivated. With AWS Certificate Manager, you can provision, manage, and deploy public and private SSL and TLS certificates for use with AWS services and your internal connected resources. Managed renewal and deployment through ACM can help you avoid downtime due to expired certificates. AWS Certificate Manager Private Certificate Authority, or ACM Private CA, creates Private Certificate Authority, or CA, hierarchies without the investment and maintenance costs of operating an on-premise CA. Your private CAs can issue end-entity X509 certificates, which are useful in scenarios such as creating encrypted TLS communication channels, authenticating users, computers, API endpoints, and Internet of Things, or IoT devices, and cryptographically signing code. These certificates are also helpful for implementing Online Certificate Status Protocol, or OCSP, to obtain certificate revocation status. ACM Private CA is for enterprise customers who are building a public key infrastructure, or PKI, inside the AWS cloud. The service is intended for private use within an organization. Certificates that a private CA issues are trusted only within your organization, not on the internet. After creating a private CA, you have the ability to issue certificates directly, that is, without obtaining validation from a third-party CA, and to customize them to meet your organization's internal needs. Let's look at an example of ACM Private CA in action. First, the CA administrator creates a subordinate CA to issue certificates. Next, the subordinate CA sends the certificate to be signed. The on-premises CA, or AWS CA, signs the certificate. And finally, ACM Private CA issues the signed certificate to resources. ACM Private CA is secured with HSMs. These HSMs adhere to FIPS 140-2 Level 3 security standards to help protect your private CA against key compromises. CA administrators can also control access to the service by using IAM policies. ACM Private CA publishes and updates certificate revocation lists to an S3 bucket automatically to help prevent the use of revoked certificates. For instance, an IoT application can check if the private certificate for a sensor is valid before accepting data from the sensor. ACM Private CA creates another S3 bucket that provides the ability to generate audit reports. Here are the key takeaways from this section. Protect data in transit by using SSL or client-side encryption when you run applications in the cloud. Use VPC endpoints to limit access to S3 buckets. The ACM service handles the complexity of creating and managing public SSL and TLS certificates for your AWS-based websites and applications. ACM Private CA can manage the lifecycle of your private certificates centrally and in a highly available way. Thanks for watching. Covers best practices to protect data in Amazon S3. All objects in an S3 bucket are private by default. Only the object owner has permissions to access these objects. However, the object owner can optionally share objects with others by creating a pre-signed URL, using their own security credentials to grant time-limited permissions to upload or download the objects. A pre-signed URL provides temporary access to a specific S3 object. By using the URL, a user can either read, write, or update the object. For example, if you have a video in your bucket and both the bucket and the video are private, you can share the video with others by generating a pre-signed URL. Similarly, if you want to receive an object from a user without an AWS account, they can upload an object by using a pre-signed URL that you share with them. To ensure that you provide the correct balance of security and operational flexibility, AWS recommends the following best practices when using Amazon S3. First, use encryption as an additional access control to complement the identity resource and network-oriented access controls already described. AWS provides a number of features that can help you to easily encrypt data and manage the keys. All AWS services offer the ability to encrypt data at rest and in transit. Next, use bucket policies along with IAM policies to protect resources from unauthorized access and to prevent information disclosure, data integrity compromise, or deletion. Set IAM and bucket policies with the least privileges. For example, if an application is expected to upload objects, then the respective IAM role shouldn't have read permissions for the object or any other permissions. Another best practice is to enable MFA delete for versioning-enabled buckets to ensure that files can't be removed or tampered with. Also, enforce SSE for each put request. This would lead to a deny in cases where the end user doesn't request SSE. And use pre-signed URLs for applications that refer to S3 objects with anonymous access. For example, downloading restricted content. Authentication and authorization must be done in the application. Here are a few more best practices. Set default encryption on a bucket if you want all objects to be encrypted once stored in the bucket. Next, while using S3 Object Lock, use the appropriate retention mode, governance, or compliance. These retention modes apply different levels of protection to your objects. You can apply either retention mode to any object version that's protected by S3 Object Lock. Also, use S3 block public access settings to enforce that buckets don't allow public access to data. Next, upload data to S3 over SSH file transfer protocol called SFTP by using AWS Transfer for SFTP. This fully managed service provides file transfer over SFTP directly in and out of S3. Using this service eliminates the need for you to manage SFTP-related infrastructure. With the data in S3, you can easily integrate it into workloads that use a broad array of AWS services. And finally, use S3 versioning to preserve, retrieve, and restore every version of every object stored in your S3 bucket. Thanks for watching. Now it's time to review the module and wrap up with a practice certification exam question. You should now be able to describe how to protect data at rest and in transit, identify Amazon S3 protection features, and encrypt data in Amazon S3. You should also be able to differentiate between client-side and server-side encryption and identify AWS services that help protect your data. Now, let's look at a sample exam question. A company requires that data stored in AWS be encrypted at rest. Which approach would meet this requirement? A, when storing data in Amazon EBS, use only EBS-optimized EC2 instances. B, when storing data in Amazon S3, use S3 versioning and MFA delete. C, when storing data in an EC2 instance store, encrypt the volume by using AWS KMS. Or D, when storing data in Amazon S3, enable server-side encryption. Note the key requirements stated in the problem. The keywords to focus on are the data stored in AWS and encryption at rest. Consider the answer choices and rule them out based on these key requirements. We'll pause a few seconds before discussing the correct answer.